In this video, we're going to go through question 14 from the NESA Sample HSC Mathematics Extension 2 exam. Question A. Let alpha equal the square root of 4n minus 2, where n is a fixed positive integer. Part I. Prove that alpha is irrational. So when we want to prove something is irrational, we almost always want to use a proof by contradiction. We want to start off by assuming that alpha is rational and then hopefully come up with some contradiction which proves that alpha is irrational. So let's make that statement. Let's tell the reader or the marker that this is what we're going to do. We're going to say suppose, and it's usually a good idea to say that we're making this assumption for the sake of contradiction. So say suppose for a contradiction that the opposite of what we want to prove is true. So in this case, that alpha is rational. And we might write it like this: alpha is an element of the set of rational numbers. Okay, so we're supposing that alpha is rational, the opposite of what we want to prove. And let's be a little bit more specific. Let's be more mathematically specific in that. What does it mean for alpha to be rational? Well, this means that we can write alpha as P on Q, where P and Q are some integers. An extra condition on Q is that it has to be non-zero, because otherwise we'd be dividing by 0, so Q is non-zero. And then there's this other statement that we add on to the statement that something is rational, which is actually really the crux of where most of these contradictions arise from. And that is that our numbers P and Q have no common factors. And a way that we can say that is that P and Q are co-prime. So we have P and Q being co-prime. Another way that we can make this statement is we can say that the GCD, the greatest common divisor of P and Q, is equal to 1. Both of those things mean exactly the same thing. You could even just write P and Q have no factors, but the main thing is that you have one of those statements there. Okay, so what do we do now? Well, what is alpha? Alpha is the square root of 4n minus 2. So let's write that in. That's equal to P on Q. And then just as we do when we want to prove something like the square root of 2 is irrational, we're going to square both sides here because dealing with square roots is pretty nasty. So we want to get rid of those square roots. So squaring both sides gives us 4n minus 2 equals P squared on Q squared. Okay, now on my left-hand side, what I want to do is I want to try to factor out a 2 here. No problem, we can factor out a 2 and we get 2n minus 1. And at the same time, I'm going to multiply both sides by q squared. And there's no harm in doing that because I know q is not equal to 0, and so certainly q squared is not equal to 0. So I multiply both sides by q squared, and I get to this statement. And just like we do when we're proving the square root of 2 is irrational, at this point, we can say that P squared is even because there's a factor of 2 on the left-hand side. So this tells us that P squared is even. And it's a very well-known fact that if P squared is even, then P is also even. And you can even try to prove this to yourself, that if P squared is even, then P is even. I think the best way of going about that would be using a proof by contrapositive. And you probably have done that in your textbook exercises as you're preparing for an exam anyway. So we've got that P is even, and let's be a little bit more specific. What does it mean for P to be even? It means that it's equal to 2 times some integer, and it's important that this number m, in this case I've called it m, but it's important that this number is an integer. Because if it wasn't an integer, if it was like a half or something, we'd have 2 times a half, which is 1, and that's not an even number. Okay, so that's why it's really important that m is even. M is an integer so that p is even. Okay, so we've got p equal to 2m. Now what we do is we substitute that back into this expression up here. Okay, so this tells us then that 2 times 2 to the n minus 1, 2 times 2n minus 1, there's no powers here, q squared equals 2m all squared. Okay, and we can continue. 2 times 2n minus 1 q squared equals 4m squared. So far, everything that we're doing looks very similar to the proof that the square root of 2 is irrational. So let's keep continuing. We can divide by 2 now, and we get 2n minus 1 q squared equals 2m squared. And now it's very tempting to write the next step, which we know from the square root of 2 being irrational, from that proof, that q squared is even. And that is true. In this case, q squared is going to be even. But we need to be a little bit more careful in this proof because there is a possibility that something could go wrong. And we need to justify exactly why q squared is even. Now, with the proof of square root of 2 being irrational, we get to this point here. Q squared equal to 2m squared. The difference between the square root of 2 and what we're doing is that we have this extra factor here, 2n minus 1. And we need to be careful because the evenness of the left-hand side, and we know it's even because the right-hand side has a factor of 2, so the evenness of the left-hand side could come from this factor, or it could come from this factor. Now, I've written already that q squared is even, but I want to justify why it's coming from q squared. And it's quite obvious actually, because 2n minus 1 is never even, it's always an odd number. So I have to actually make that justification on the side as I'm continuing, otherwise the proof isn't actually very rigorous. So this is saying q squared is even since 2n minus 1 is guaranteed to be odd. This is always odd for every integer value of n, which means that this can't have a factor of 2, which means the only place that this factor of 2 could come from is from the q squared. Excellent, so we've got q squared is even, which means that q is even, just like we saw above with p squared being even. So we've got these two lines here. We've got that p is even and q is even. Now, if p is even, that means 2 is a factor of p. And if q is even, that means 2 is a factor of q. And this gives us a contradiction. So I'm going to label this as line 1 and line 2. And I'm going to say 1 and 2 produce a contradiction. They're producing a contradiction. And I'm going to even tell the marker what the contradiction is. Contradiction. Since they both, or maybe I should even be more specific, since p and q both have a factor of 2, or maybe say both have 2 as a factor, but in our assumption, they are coprime. P and Q were coprime. So we've got our contradiction. And it's really important that when you get a contradiction, that you write a statement like this. Make sure the reader knows exactly where the contradiction is coming from and what it is in your assumption that you're contradicting. In this case, we're contradicting that P and Q are coprime. So we've got our contradiction, and we can say, therefore, alpha is not rational, and maybe we can even write it in words now. Alpha is irrational. And this is the end of our proof. We can indicate that by a little square like this. There's multiple ways to indicate the end of a proof, but this is what I use. And that's the end of part I. Let curly brackets beta denote the fractional part of beta. So beta equals k plus curly brackets beta, where k is an integer and the fractional part of beta is between 0 and 1, but not including 1. Part 2. Let capital N be a positive integer and consider the following numbers: 0, fractional part of alpha, fractional part of 2 alpha, all the way up to the fractional part of n alpha. By dividing the interval 0 to 1 into sections or otherwise, prove that at least 2 of these numbers differ by less than 1 over n. All right, now when I read a question like this, and it's asking me to prove that at least 2 numbers, or at least 2 of something is happening, I'm already thinking about Pigeonhole Principle, because I know that questions that involve at least 2 of something happening usually require an application of the Pigeonhole Principle. But the question is, how do we use it? How do we apply it? Now, the question itself has actually given us a bit of a hint. It's saying by dividing the interval 0 to 1 into sections. So what I'm going to say is to consider the following partition. So consider the following partition. Now, a partition is just a fancy word for saying a way of dividing something. It's especially used in mathematics. Not really sure about its use outside of mathematics, but definitely we use it in maths. A partition. So what is our partition going to look like? Well, keeping in mind that I want to prove that the difference between two numbers is less than 1 on n, I want to split up my interval 0 to 1 into different sections where the gap between any two numbers in each section is always going to be less than 1 on n. So what do I mean by that? Well, just have a look at this. We want to start off by looking at from 0 to 1 on n, and I don't want to include, that's why I've got an open bracket here. I don't want to include 1 on n, because now any two numbers in this set are guaranteed to differ by less than 1 on n. I want to do the same for this next set. It's going to start at 1 on n, and then it's going to end at 2 on n. Now you can see, again, I've got an open bracket here and a closed bracket here. This open bracket means that 2n is not included, and so any two numbers in this set also differ by less than 1 on n. And I'm going to continue doing this all the way up to the number 1. So this will be 3 on n, open bracket, dot, 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 all the way up to, I think this one will be n minus 1 on n, up to 1. And I'm going to include 1 here. But this is not going to be a problem for us because we know that our fractional parts can never be 1 anyway. They're strictly less than 1. So when I prove, and what we're going to do, we're going to use the pigeonhole principle to prove that there's going to be at least two elements from this list in one of these sets here. If it was the case that they're in here, it doesn't matter anyway that this is included because these numbers can never be equal to 1. So it's basically not included for these numbers anyway. Okay, now let's think about it. How many numbers do we have here in this list? Well, we start at 0, so that's our first number, and I'm actually going to number these. This is our first number, this is our second, and our third. And what you should be able to notice is that the position in the list is always 1 more than the coefficient of alpha. So here, this is the second number, the coefficient of alpha is 1. This is the third number, the coefficient of alpha is 2, and so on. This up here has a coefficient of n, so it's the n plus 1th number in our list, which means that we have n plus 1 numbers in this list. So let's actually say that as part of our solution. Since we have n plus 1 numbers, and maybe let's label this in the list star, and let's call this one here double star. And we only have how many sets here? Well, here's one set, here's the second, here's the third. Let's again label them. This is our first little set, this is our second set or interval, this is our third interval. This would be, now you can see that the number is matching up with what's on the end here. And we can rewrite this number 1 as n over n. So this would be the nth interval here. So we've got n intervals here in double star. So let's start again. Since we have n plus 1 numbers in the list star, and we only have n intervals in double star, by the pigeonhole principle, now I'm going to write PHP, but please don't do that in an exam. Actually write out pigeonhole principle. But by the pigeonhole principle, there are at least two numbers in at least one of the intervals. And since we were very clever in the way that we set up our partitioning, if we have two numbers in this set, then they're guaranteed to be less than 1 on n. The difference between them is guaranteed to be less than 1 on n. And we can say the same for any of these intervals. So therefore, or this implies that there are two numbers, at least two numbers, whose difference is less than 1 over n. And that's the end of our proof. Part 3. Hence prove that for any positive integer n, there exist integers p and q such that 0 is less than the absolute value of q alpha minus p, which is less than 1 over n. Alright, so the question says, hence prove that, which means that we want to start using the stuff, or eventually we want to use the stuff that we worked out earlier, or that we proved earlier. Now, what I've done is I've written down this list of numbers, which was dealing with the fractional parts of these multiples of alpha. And what did we prove in part 2? We proved that at least two of these numbers here differ by 1 over n. Now, this idea of differing by 1 over n seems pretty good because this looks like a difference of something being less than 1 over n. All right, so that looks like a link that we're probably going to have to make. Now, let's just go over it one more time. What we proved in part 2 was that at least two of these numbers differed by 1 over n, which means that we can find two numbers in here, any two numbers, well, not any two, but we can find two numbers that differ by 1 over n. So, by part 2, that means that there are some integers in here, and I'm just going to call them x and y. So by part 2, there exist integers x and y, and both of those are going to be less than or equal to n, because they can't be greater than n, otherwise it's not part of our list. It would be like going this way in terms of the pattern of the list, and that's not on our list. So they're less than or equal to capital N. So we've got these two integers such that x alpha, the fractional part of x alpha, minus the fractional part of y alpha, the distance between them, because we don't know which one's bigger than the other one, so this difference here could be negative, but we don't care, we just care about the actual distance between them, is going to be less than 1 over n. Okay, and this is basically the result that we proved in part 2. Now this is starting to look good. We've got an absolute value. It's being less than 1 on n, which is what we want here. But we can also see that we also need it to be greater than 0, but of course any absolute value is greater than 0, so we can just add that in like this. Alright, now what are these things? We can see that inside our absolute value, we've got these curly brackets. We've got the fractional part, but in what we want to prove, we don't actually have that. Okay, we've got just the alpha. So let's think about how we can rewrite this in terms of something with just alpha. So I'm going to do this in green here. I can say by definition, we've got x alpha equals some integer part, I'm going to call it k1, plus the curly brackets x alpha. And we also have y alpha equals k2 plus the curly brackets of y alpha. And if I was to rearrange those, actually before I do any rearranging, I might say that k1 is an integer, and same with k2 being an integer. I'll rearrange both of these statements to make the fractional part the subject, and I get curly brackets x alpha equals x alpha minus k1, and similarly here I get y alpha curly brackets equals y alpha minus k2. Now I'm going to substitute these two results now into these two ones. I'm going to substitute them in here, and that'll eliminate any curly brackets that we see. Alright, so what do we have? This tells us that 0 is less than the absolute value of, I don't need curly brackets anymore, x alpha minus k1 minus y alpha minus k2. And that's less than 1 on n. Now, what I'm going to do is I'm going to collect like terms. I'm going to do this step in these two steps in one. I'm going to expand out this negative here, and then I'm going to collect terms that have an alpha and collect terms that don't have an alpha. So what I get is 0 is less than, let's see, x minus y alpha minus k1 minus k2 is less than 1 on n. You should convince yourself that that's true. But then I'm just going to relabel these things. I'm going to label this x minus y. I'm going to call it q, since that's what I want it to look like. And similarly, I'm going to call this thing p. So this tells me that 0 is less than q alpha minus p. It's less than 1 on n. And I'll tell the reader what q is, where q equals x minus y. And since x and y themselves are integers, this thing is an integer. And also, p is equal to k1 minus k2. Since k1 and k2 are integers, their difference is also an integer. And so I get my final result. I can put my box to indicate the end of my proof. Part B. A particle is thrown from the point O at the top of a very tall building. The equation of motion is s double dot equals minus r s dot minus g times j, where s of t equals x of ti plus y of tj, and that is the position vector of the particle at time t. R is the constant, or is a constant, and j is the magnitude of the contribution to the acceleration in the vertical direction due to gravity. The initial conditions are s of 0 equals 0, and s dot of 0 equals u cos alpha times I plus u sine alpha times j. Question I. What is the physical interpretation of the constants u and alpha in the expression for the initial condition s dot of 0? Alright, so I've written down all our information that was given in the question. So that is the equation of motion and our initial conditions here. And I've also drawn a bit of a diagram so that we can add things on if need be. I always find it's really important to be able to add things onto a diagram in a question like this. In fact, in any mechanics sort of question. Now, what do we want? We want to understand what u and alpha are. And it's telling us that they're coming from this initial condition here. So this thing here, s dot, is the initial, or s dot at 0 is the initial speed, the initial velocity vector. So that means if I wanted to draw that in, it would look something like this. This is our initial velocity vector. Now we can decompose that into its x and y coordinates, or components rather, and it's given by these two values here. So the x component is going to be like this, and that has value u cos alpha, and the y component is this part of our vector, so it'll look like this, and then again it has value u sine alpha. Now by a little bit of trigonometry, I think it's fairly simple to see. If I wanted to, now it is a right angle triangle, so if I wanted to use Pythagoras' theorem, I can do that on the side here. If we called the length of this vector here, if we just called that c, since it's the hypotenuse, then the length of c squared is going to be u squared sine squared alpha plus u squared cos squared alpha. And of course, if I factor out the u squared, I get u squared sine squared alpha plus cos squared alpha. Of course, sine squared plus cos squared is 1. And so u squared is equal to the length of this vector here. Taking the square root gives us u. Of course, we take the positive value because we're just thinking about the magnitude here. So this length here, instead of c, I could actually just write that length as u, or that vector as u. So u is the initial speed. Okay, we're only talking about a magnitude, so it's not velocity, it's speed. So u is the speed of, or the initial speed of the particle. And what's alpha? Well, alpha is just the angle in here. Okay, and that's just basic trigonometry. sine equals opposite over hypotenuse and cos equal to adjacent over hypotenuse. Both of those would give you that as our angle alpha. So if I want to write my answer, I will say u is the initial speed. So initial speed, again, speed and velocity. We want to use speed here because we're only talking about magnitude. And for alpha, we can say alpha is the angle between the initial velocity vector and, that doesn't even look like an alpha, so let's write it properly, between the initial velocity vector and the horizontal. Or if you want, you could write is the angle at which the particle is projected. So the angle at which the particle is projected. And that's the end of part I. Part 2. By considering the horizontal equations of motion, find an expression for x of t. Okay, so here are our equations of motion here. We've got acceleration equals minus r, the velocity, minus g times the unit vector j. And we've also been told that s of t, which is the displacement vector, is x of t I plus y of t j. Okay, so not much is going on here. But let's just get a think about what this is really telling us. Let's try to understand what's going on. We've got our minus gj, which is saying we have the acceleration due to gravity and it's negative, which means it's going downwards. That's what we usually expect. But we've also got that the acceleration is proportional to minus the velocity. And this is really telling us that this is a resisted motion problem. Okay, there's some resisted motion and it's given by this part here, minus r s dot. Okay, but we just want to work out what x of t is. So let's try to pull out what the x component of this differential equation is. Because this differential equation really is two differential equations. It's one in terms of x and one in terms of y. But we only want the x component. So let's write it in a different way. Firstly, what is s dot? Well, s double dot equals minus r. S dot would be differentiating s. So that means we need to differentiate this thing. So that's going to turn into x dot of t times I plus y dot of t times j minus g j. If we collect everything that's got to do with j's and everything got to do with i's together, we get the following. Minus r x dot t times I plus, and I'll put this bit in brackets, minus r y of t minus g times j. So now we can clearly read off that this is the x component of the acceleration and this is the y component of the acceleration. Since we only want to look at the x component, we can therefore say that x double dot of t, the acceleration in the x component, is equal to minus r x dot of t. And now this is just a differential equation which we need to solve. Now the way to go about this is to divide by x dot of t. So let's do that. X double dot of t over x dot of t equals minus r. And now we want to integrate both sides with respect to t. So when I integrate, I have x double dot t over x dot t dt. That's equal to the integral of minus r dt. Now on the left-hand side, I have a fraction where in the denominator I have some function, and in the numerator I have its derivative, because the derivative of velocity is acceleration. So this means that when I integrate it, it's going to be log of the denominator, x dot t. My right-hand side, well, the question tells us that r is a constant, so I'm just integrating a constant with respect to t. That becomes minus rt. And since I have no more integrals, I'm going to add a constant on. And I'm going to call this constant c1. I'm labeling it c1 in anticipation of having to do more integration, where I'm going to get another constant popping up. Okay, but we want to get x by itself. So that means we first have to get x dot by itself. So let's exponentiate both sides to get rid of the log. That gives us e to the minus rt plus c1. We're going to split this up as the following, using our index laws. But if c1 is a constant, well then e to the c1 is also a constant, and so I can just call that thing a. So I'm just going to call this a e to the minus rt, and I'll probably label here that a equals e to the c1 is a constant. So I'll just write it on the side so that the reader knows what's going on here. So I've got x dot t equals a times e to the minus rt. Now we'd like to work out what that a is, and we can do that using our initial conditions. So if we go back up to where we wrote our initial conditions, this is the initial condition for the velocity, so the x coordinate of the velocity. So when time t equals 0, x dot is equal to u cos alpha. So let's use that condition here. When t equals 0, x dot of t, so x dot 0 equals u cos alpha. So we plug that in to this equation here. What do we get? We get u cos alpha equals a times e to the negative r times 0. This expression here is just 1, so I've got a times 1 equals u cos alpha, which means a equals u cos alpha. So that means we can now substitute that back into here, and we can write that x dot of t, the velocity in the x direction, is given by u cos alpha times e to the minus rt, which is good. We've got an expression for x dot of t, and we can integrate that to get x of t, which is what we want. So x of t is going to be the integral of this thing. So the integral of u cos alpha e to the minus rt dt. Now, at first quick glance, this looks pretty horrible, but then you look a little bit more closely and you realize that this part here is not dependent on t at all. So in fact, it's a constant, which means that I can pull it outside of my integral, and the integral really is just integrating this exponential, and exponentials are quite easy to integrate. So when we do integrate this, it becomes u cos alpha times e to the minus rt over minus r plus a constant, and this one I'm going to call c2. And again, I need to work out what c2 is, and I use my initial conditions to do that. If we go back to our initial conditions, we know that initially the particle is at the origin. That's what this part here is saying. It's initially at the origin, so we can use that bit of information. When t is equal to 0, x of 0 is 0. And if we plug that in, we get 0 equals u cos alpha times e to the minus r times 0 over minus r plus c2. Rearranging to get c2 as the subject, this becomes u cos alpha over r. Of course, this term up here in the numerator is 1. So now we can substitute this back into our expression for x of t. When we do that, we get x of t is equal to u cos alpha times e to the minus rt over minus r plus u cos alpha over r. This is our final answer, and this would be correct, but we can write it just a little bit more neatly than this. We can factor out u cos alpha on r, and then what we'd be left with is negative e to the negative e to the negative rt plus 1. I'm just going to write that in the other way, in the opposite order. So we have 1 minus e to the minus rt. And that is the end of part 2. Part 3. Verify that y dot t equal u sine alpha e to the minus rt minus g times 1 minus e to the negative rt over r satisfies the acceleration equation and initial conditions. Okay, so notice that the difference between part 3 and part 2, in part 2 you actually had to derive your expression. In part 3 they've given you the expression and they just tell you to check that it satisfies these conditions that we've written down in blue. So with part 2, we actually had to integrate starting at this expression for the acceleration in the x component, and then we had to integrate. Now we don't. We just have to start with this and differentiate to see that we get to this point here, which I think is a little bit easier to do. So let's differentiate. Y double dot of t equals, now differentiating this first bit here, u sine alpha is a constant, it's got nothing to do with t. So when we differentiate it, we're really just differentiating this, and that brings down the minus r. So minus r u sine alpha, we don't need a bracket, e to the minus rt, minus, now we want to differentiate this bit. The g on r is just a constant that we're multiplying by. So when we differentiate, it really comes down to differentiating what's inside this bracket here. And when we differentiate that, we get positive r e to the minus rt, of course over r. Now convince yourself that that is correct. Okay, so now we've got our derivative. The entire aim of the rest of this part is to show that what we've got is equal to this, or it's in this form, minus r times y dot of t minus g. Because then it would be, then if it was equal to this, it would satisfy the acceleration equation, or the differential equation for acceleration. All right, so what do I notice when I look at this equation? I can see that I need to have a minus r times y dot of t. So I really need y dot of t to reappear in my equation. Okay, so what I'm going to do, I'm going to try to force that to happen. But before I do that, I'm going to factor out this minus r. So let's factor out the minus r. If I factor out a minus r from the first term, I'm left with u sine alpha, e to the negative rt. And if I factor out a minus r from this second term, well, here's the minus and here's the r. So that gets factored out, and I'm left with plus g e to the negative rt over r. Okay, now this still, it's looking better, but it's still not there, because we can see that with y dot of t, if we want that to reappear, we need to have 1 minus e to the negative rt appearing here, but we really only have e to the negative rt. So what we'd like to have is the 1 minus business going on. So what we're going to do is we're going to add 1 to the numerator, and we're going to subtract 1. But before we do that, I'm going to do this in 2 steps, just so everyone can see exactly what's happening. But in an exam, I would probably only do this in 1 step, just to save myself time. I'm going to write this positive fraction as minus minus. So it's going to be minus g times negative e to the minus rt over r. I'm going to write my r's a little bit neater. The reason I've written it like this is because I can see up here it's really a minus exponential, where up here we had a positive, or down here we had a positive exponential. So I really wanted that minus exponential to appear. Now I can do that trick of adding 1 and subtracting 1 on the numerator. So we've still got this u sine alpha e to the minus rt minus g times, let's add 1, and that looks good because that's exactly what we've got up here, what we're going for. But then we can't just add 1 for nothing, we also have to subtract 1 to compensate for that. Okay, next step. To make it look exactly like y dot, we have minus g. We're going to distribute the minus g to through this bracket, but in a certain way. I'm going to put imaginary brackets, and you can even put them in if you want to. Brackets like this. We're going to distribute the minus g to that green bracket and then to the negative 1. So to the green bracket gives us the following. Let's do it in black. 1 minus e to the minus rt, and then we have minus g times negative 1, which is going to be positive. Well, firstly, this is over r, and then we have positive g on r. Okay, this is good because this entire term here is just y dot of t. So I'm going to rewrite that as y dot t, and that's basically what our aim was. We forced that to reappear. So we've got minus r, y dot t, plus g of r, and then we just distribute the minus r through this bracket, and we get minus r, y dot of t minus g. Okay, so y dot of t satisfies the acceleration equation. Good. Now we also need to show that it satisfies the initial conditions, which is not too hard. We just have to substitute t equal to 0 in here. So when we do that, this term here will become 1. This term will become 1, and we'll have 1 minus 1, which becomes 0. So this entire term here becomes 0. And then we have u sine alpha times 1 minus 0, which is u sine alpha, which is exactly what we have here. Now I'll quickly just do that a bit more formally. So when t equals 0, we've got y dot of y dot of 0 equals u sine alpha times e to the power 0 minus g times 1 minus e to the power 0 over r. And so this is u sine alpha times 1 minus 0, which is u sine alpha. Okay, and then that checks out, that satisfies the initial condition. And that's the end of part 3. Part 4. Find the value of t when the particle reaches its maximum height. Okay, so this is the result that we showed satisfied the differential equation. It's the result for y dot of t. And we know that the maximum height occurs when y dot t is equal to 0. So we would write max height when y dot of t is equal to 0. So basically what we need to do here is we need to solve this expression equal to 0. So let's go ahead and do that. We have u sine alpha times e to the negative rt minus g into 1 minus e to the negative rt all over r is equal to 0. Now we want to solve for t, which means we want to make t the subject here. And we can see that we have an e to the negative rt here and an e to the negative rt here. And that's the only place where t appears. So we want to group those together and get everything else onto the other side. So if we were to expand out this section here, what would we get? Well, we start off, we still have this e to the negative rt u sine alpha term here. Then we would get minus g on r plus g on r e to the negative rt equal to 0. Now, in the one step, I'm going to factor out an e to the negative rt from both sides here, and then and bring this term over here and make it a positive. So, factoring out, we get u sine alpha plus g on r multiplied by e to the negative rt equals g on r. And now what we would typically do, because we want to get t by itself, we would divide by this term. However, I'm going to be a little bit sneaky here, and I'm going to multiply both sides by e to the positive rt. And you'll see why in a moment. So when I do that, and I think at the same time, I'm also going to multiply by r over g. So I'm going to write on the right-hand side what I'm multiplying by. I'm multiplying both sides by r on g e to the negative rt. So this would give us u sine alpha plus g on r. When I multiply by the positive e to the negative rt, and I wrote it as a negative, but it should have been a positive. When I multiply by the positive e to the rg, that's going to cancel with the e to the negative rt, and I'd be just left with r over g. And then on the right hand side, I have just e to the rt. Now, if I distribute this term through both of these terms in the brackets, I'll get r u sine alpha all on g plus 1 is equal to e to the rt. And now I'm just going to take the log of both sides. So log of ru sine alpha on g plus 1 is equal to r times t. But then if I just divide through by r, I get t. And so this is our value for t. And that is the final answer. Part 5. Calculate how far you must be from the point at the base of the building directly below O, the origin, to ensure that you cannot be hit by the particle. Give your answer in terms of the constants specified. Okay, so since we're dealing with a horizontal distance, I've written down the expression that we worked out in part 2 for the horizontal displacement x of t. It was equal to this thing here. That's the one that we derived. And I've got this diagram that we were having a look at the very beginning as well. Now we want to be standing somewhere down here, and we want to find the distance from the base here to where we're going to stand so that we can be 100% sure that this particle never hits us. Now in the question, we don't know how tall this building is that the particle is being projected off of or thrown off of. And we also don't know how long it takes for the particle to reach the ground. We don't have that in terms of some time. It could take 10 seconds, it could take maybe 100 seconds, who knows? The idea is that we don't know. So we don't have a value of t to substitute into this expression. Now, one thing that we need to observe here is that this part is a constant, so that's fine. This bit here is really what's going to determine how far the range is with regards to how long it takes. Now, we can easily see, or maybe not easily see, but with a bit of thought, we can see that this function here, 1 minus exponential to the negative RT, this is a monotonic increasing function. So I'm going to write that here in purple. This thing here is monotonic increasing. Now, why is that important? Well, what it means is that the distance, the horizontal displacement rather, as time progresses, as time gets further and further along, the horizontal distance is always going to increase, which means that our particle is going to go like this, but it's never going to do something like this. It's never going to turn back and then come like this. And then maybe it will turn back again. The idea is that it always continues like this. And that's really important. So we don't know how long it takes for our particle to reach the ground. But if we have a look at what happens when t goes to infinity, that's going to be the absolute maximum distance that the particle can travel in the horizontal component. So what we're going to do is we're going to say, let t approach infinity, and we get x of t equal u cos alpha on r, 1 minus, what happens to this thing when t approaches infinity? This is e to the negative infinity, and e to the negative infinity is like 1 over e to the infinity, which is 1 over a massive number, which is going to be 0. So this becomes 0 here. Maybe you can justify that by saying that the limit as t approaches infinity of e to the negative rt is equal to 0. And so then, of course, this value is just u cos alpha over r. So if we stand at a distance of u cos alpha over r away from the base here, we're 100% guaranteed to never be hit by the particle, no matter how long it takes for the particle to reach the ground. And that's the end of part 5 and the end of question 14.